Hello and welcome to an overview of exploCFD version 7. This is the latest version released in 2020 amid the COVID-19 crisis. We're going to go through just basically how the software operates so as to give you an overview of how things work. And it's still basically the same mode of operation. The way that the software works is basically you read in a PDF of a plot plan or an offshore platform or an FPSO, what have you. Usually it's a top view, but it can be a side view, and sometimes those are very useful. You can select the domain to be either the entire plot plan or part of it by controlling things, and then when you're ready to go, you can set it to run, and the way that it runs basically is it's a hybrid code. So the code will first analytically estimate the source terms. So if you're doing a gas explosion, it uses CSC, the confinement specific correlation, which has been proven to be far more accurate than the multi-energy method because it's able to decouple confinement from congestion. It also does BLEVEs. It uses the method by Prue from 1991. Basically, he's converting that into a TNT equivalent explosion. You could do a TNT equivalent explosion if you're doing something like ammonium nitrate or an improvised explosive device like a terrorist activity type of device. Or you could do a dust explosion where you put in the KST and the gas cloud. Or you could even prescribe a pressure. Like, for example, in mining, a common problem in mining is the explosion of tires. So for that, you don't need any combustion or any BLEVE parameters or any dust explosion parameters. What you do need is just the pressure of the tire at which it ruptures. And so you can do that as well. So it's got a lot of versatility. Pretty much anything that explodes will be programmable in this. Once you calculate the source, the strength of the explosion, that is then passed on to SU2 or open source CFD software, and that allows you to propagate the explosion into the wider domain. And we'll show you exactly how that works for several examples. It's run in a 2D fashion. This is deliberate because SU2 runs in a 3D way, so you can configure SU2 to run on detailed 3D geometries. There's no need for that, and in fact, CFD softwares have traditionally been for explosions. All of the CFD softwares have been traditionally dissipative, and so to not be on the underconservative side, SU2 is configured in a 2D simulation. So you're basically solving at the ground level, and then the output is visualized with PowerView, very powerful visualizing tool that shows you exactly how your explosion is interacting with the rest of the domain. Let's talk about gas explosions. In the past, to do a gas explosion using CFD, you basically had to model the site in 3 dimensions. That's expensive, it's time-consuming, it may not always be possible, and in fact, the end result of 3D CFD used for explosions has a large uncertainty, and this is something that we don't discuss too often, but there's a 30-50% even order of magnitude sometimes uncertainty for the state-of-the-art CFD. So it pays to be conservative and to try and stay within the sort of limits or the uncertainties of 3D CFD, and that's the approach that we've taken to actually model this. So instead of doing all of that, software now relies on just the plot plan and simplifies things and stays within the uncertainty. We'll get to that in a minute. But if you were to, as bad as CFD is in terms of uncertainty, apart from CSC, the multi-energy method, for example, is even worse. And in fact, we have a paper from 2010, I believe it might be 2014, where we looked at a comparison of the gain correlation, that's guideline for the application of the multi-energy method, and that's used in softwares like FAST, and we compared that to CFD. And had there been a correlation between two methods, then all of these points would be sitting on the line. Obviously, they're not. The R squared for the two, or R squared between the two, was 0.3. By comparison, one of the PhD students out of UWA actually came up with a much better method. Again, it's an analytical estimate, but this is how it compares to CFD. And it's been compared over about 3,000, two sets of 1,500 cases. And you can see here, the R squared here was about 84%. So this method is what is used for gas explosions as the source. Other methods for dust, we use obviously the standard method that it uses KST and the volume of the gas cloud, or the volume of the vessel, and that's listed in many papers, that method. I think it was first mentioned by Nagy. So we also use the TNT equivalency method for other cases, things like ammonium nitrate or improvised explosive devices, terrorist attacks, and so on, where applicable. And the method that we use, or the source for that information, is U.S. Army TM5 1300. It's basically this figure 27 that is sort of digitized into the software. That's as far as the analytical methods go in terms of calculating the source of the explosion. It's then fed into a CFD software, SU2, which is an open source software out of Stanford. You can try, and we'll show you exactly how it works right now. So basically, the software is very easy to load. You can basically just load a drawing. This is a normal plot plan of an area. You could see it's picked up all the lines, and you could select and deselect the lines. So in this particular case, we have an explosion on an FPSO off the coast of this is in Brazil, actually, off the coast of Brazil, the south of Brazil, and you've obviously got some industrial facilities here, some important sort of storage tanks here. More importantly, here, a kilometer away, there is a sort of residential area, and so it's easy to select and deselect walls or lines to be treated as walls. So, for example, this line here demarcates the shoreline. You don't want that to be treated like a wall, so you can see you can easily deselect it, and it goes purple or gray in the software. And you set up the parameters, which is very easy to do for the gas explosion or the BLEVE or the TNT explosion. You set up the gas cloud, and when it's done, it outputs the shock wave, the explosion that's coming out from the vessel. Other examples we have here. This is a redo of Bunsfield. You could see the explosion on 3 Cherry Trees Lane coming out towards the buildings. And one thing that you notice about this is you could see the reflected shock wave. If you look over here, you don't see this in normal or in other CFD softwares. You can see the reflected shock wave very clearly. Again, look over here. When the shock wave reaches the tank, you'll see the reflected pressure on the tank very clearly. And this is because we don't turn it into a porous medium or anything like that. You see that shock wave reflecting off the tank, very clear. So there's a high resolution capture. This is an ammonium nitrate explosion that's occurring on a site, and you could see it interacting with the walls, with the facilities, as the explosion propagates. Obviously, the pressures are extremely high in the case of an ammonium nitrate explosion. All these are prior real cases for clients. This is a BLEVE in an industrial facility. This is a tank undergoing a BLEVE. I think, to my knowledge, exploCFD is the only software in the world that actually models an ignition of a flashed flammable vapor on top of the BLEVE. So the BLEVE is actually the rupture of the tank, and there's a flash and an overpressure that's created. But on top of that, the released chemical may be ignited, and exploCFD is the only software that actually models that as well. It could make a very big difference in terms of overpressure. You could go from half a bar to 10 bar. If the tank were in a congested area and releasing a high energy material. We've done a lot of validation on this. As I said, the components are heavily tested. CSC and the other analytical methods have been heavily tested. And also, we've been looking at the integration of all of these components together. So these are the Defects repeatability tests, and you can see agreement here as the shock wave propagates outwards from the source of the explosion outwards. This is about as good agreement as you're going to get from any explosion modeling software, 2D, 3D, or any other type. The software performs as well as you might expect, and of course we continue to keep testing it and pushing its limits and seeing how far, where you can and where you can't use it. But it's very easy to use, and it's a quick, rapid solution, and that's one of the more attractive features that it has. It certainly beats the sort of concentric circles that you get with other analytical methods, where the walls, the obstacles, the other features of the geometry are not taken into effect, or some method that just interprets CFD results, or interpolates CFD results. That's you don't know where you're sitting as far as the accuracy of that is concerned. This is a method that interacts with changing problems, so you can adapt it to cases, geometries that you have never seen before, and that is a very important feature. Thanks for listening, and we hope to see you trialing our software soon.